So I said we will do some simple simulation on MATLAB how Poisson equation is going to pan out. We did a lot of mathematics now, but let's look into a practical way of solving this using MATLAB. So MATLAB luckily has some of the inbuilt functions which gives you easy way to get certain results of matrices manipulation. So I'm going to use that to make things simple, but the goal of this demonstration is to show how the entire field distribution, whether it is potential or if it is electric field, is going to change as a function of the discretization itself. So with that in goal, let's look into the solver which I have got. So it's based on the material that is freely available online, particle in cell. So I have a Poisson solver on a circular domain, and the Poisson equation is given as uxx plus u of yy is equal to the square root of certain value. So the rho value, which is nothing but the surface charge density, is going to depend on x and y. So that's the idea, and there is an analytical solution that one can derive for this, but let's go into the step one by one. So the Poisson equation is of the form k of u is equal to f. Remember, in our earlier example we said it will be k of phi is equal to b. What the code actually does is, first it generates a triangular mesh over a region, and for this I am going to use the mesh generator which is called as the dish mesh. So it's freely available online, so it's going to give us certain mesh which is based on the amount what we are putting in. So if I say my discretization is going to be h naught, so if I say my edge length is going to be certain number, so it's going to generate the edges of that length. And what is interesting here is I am going to give also the starting and ending point, so the bounding domain. So the bounding domain is going to be the x minimum and y minimum and x max and y max. So once I give that, it's going to give me a domain with certain grids. So let's see how it does using this example. So first it generates the mesh, and then it goes into the K matrix assembly. Remember, I explained you how the K matrix is done step by step. We take each of the local element and then we put them on the global matrix and we construct the entire matrix. So that's what we are going to do here, and after that I am assigning certain boundary condition, which is I am saying Dirichlet boundary condition, and I am assigning the value of the potential unknown to be 0 on those boundaries, and then I am trying to solve the Poisson equation. So I am going to show you how the domain itself is going to look like based on the input values I am giving here. So the domain bounding values are here, the minimum value of x, the minimum value of y, the maximum value of x and maximum value of y. I make a functional stop here so that you can see the simulation and the domain itself. Let's put 0.8 and see how the discretization is going to look like. This is not a very good discretization. The reason is I say the starting and ending point is minimum value is -1 and the maximum value is 1. So inside a particular domain I can have maximum only 2 cells, because 0.8 plus 0.8 is going to give me 1.6, and the domain maximum limits is going to be 2, so it's not very good. So putting it 0.8 is going to be a very coarse discretization. So having 0.8 is not a good solution, so I am going to refine the mesh by reducing the edge length to 0.5. So once I have 0.5, let me see how the domain is going to look like. You can see the length of each of the edges is going to be approximately 0.5, and based on that the dish mesh is going to give me domain. And of course what you also see is the domain is no longer circular. In the initial case it was really bad, but here you see that it's conforming more and more to the circular area. So what I'm going to do is I'm going to keep 0.5 as my domain discretization, maximum edge length, and I'm going to run the code without stopping it and then see what will be the result of the simulation. So basically I said I have defined the domain, I am assigning the K matrix to be 0 initially, and I am going inside each of the triangular elements, each element at a time, I go and load the values one by one, and then I compute the value finally, and I know the integration. I integrate it over each of the triangles to get the value of f, which is on the right hand side, and finally I am going to invert the matrix by solving this equation. So initially it is going to be k of u is equal to b, and I can get the k inverse by this MATLAB function. So let's run this code and see how the result is going to look like. So what you have got is, you have got a very crude discretization, and the maximum is at the center, the row maximum is at the center, and for the function what we have chosen, the value of rho is going to change as a function of minus square root of x square plus y square. So it's going to be a circular charge variation, and you have the equipotential lines which are circular lines. That's what you see, and that's how it should look. So let's go to point 3. So the maximum edge length is going to be 0.3 now, and I'm running the same program. So you see the value is getting more and more finer. You see the nuances of the equipotential areas. Initially when we had 0.5, we didn't really see the green equipotential line. We start to see it now. So if I refine it even further, let's say I'm going to 0.2, I might be able to see more refinement, and likewise I can go to 0.1 also. So you are able to see the various accurate results for various discretization. Obviously the more finer our element dimensions are going to be, the domain is going to be accurately also represented. So what we have demonstrated in this example is to get a physical sense of how the potential fields are going to be, and also how to do it in a simple way using MATLAB. In the beginning, remember I said one thing is missing, which is the time domain approach of the Maxwell equation itself. So that is what we will focus in next part of this module, and we will start with the Maxwell equation itself and in time domain, and we will model it for the finite element approach. So let's start with the basic Maxwell equation itself, which is given by the two curl equations. So the curl of E is equal to minus mu H, and the curl of H is equal to epsilon d by E plus J. So what we have said now is we are going to start with these two curl equations. Now obviously there are going to be the divergence conditions. The divergence of B is equal to 0, and the divergence of D is also, we have set it to 0, and we can start manipulating the second equation. So let's say this is 1, this is 2. So our approach is we are going to go for finite element time domain. So what we are going to do is, from 2 we have 1 by epsilon of H minus d by dt of E is equal to J by epsilon. So this is 3. So I am going to multiply 3 by the curl. So I am going to multiply equation 3 by curl. So curl of 1 by epsilon of H minus is equal to 1 by epsilon A cross J. So for two dimensional problems, let's say we will start with a simplification that we are only interested in the xy plane, and your magnetic field is going to have only the z component. So it's going to be a transverse electric case. So we will reduce this entire equation into more simplified form. So we will use the simplified equation. So we are going from here to the form that we have got for the transverse electric case. So this equation can be written using the values of the curl. So I have the curl value which is here, I am going to substitute it here and write it in the value which is only in terms of h. So what I will have is of 1 by epsilon curl of h plus mu d square dt of h plus mu sigma of E d t h is equal to 1 by epsilon curl of j. So what I have done is I have used the value here and I have exchanged the value for the E using the expression which is here. And what I have also done is I have made the right hand side as j and I have kept the source as the j function. So what we have got is 1 by epsilon r epsilon naught del square hz minus sigma mu r mu naught epsilon r epsilon naught dt of hz minus mu r mu naught d square h z equal to minus 1 by epsilon r epsilon naught. So this is a simple equation where the coefficients have to be assigned. So what we can write as this is a second order equation in time. So what we see is a second order equation in time. So I can write it as some T matrix multiplied by, let us say, the second order equation in V plus some B matrix multiplied by first order derivative of V with respect to T plus some G matrix into V itself plus some forcing function which is F equal to 0. So this entire expression can be written in this form where V is some coefficient vector so what you see here is this P is actually the coefficient vector for Hz. We are using this as a coefficient matrix. So what you can see here is this are the values and F is going to be directly given for the value of J. So J is the forcing function and for which you have F. So what we have written is basically an equation that is second order in time derivative and we have written it in this form. Obviously we haven't said anything about T, B, G and F. So we will see the value of T which is in this equation is going to be given by a second surface integral. So it's in 2 dimension. So you have the x and y integral of mu r by c square wi wj dx dy. So wi and wj are the weighting functions in I and j, so in x and y direction respectively. Similarly what we are going to have is we are going to have the value for b of j which is in this part is going to be the equation for this one which is given by the double integral. So one for x and one for y, it is going to be mu r divided by c square 2j omega c plus alpha wi wj xy. Similarly we can also have the expression for j so on and so forth. So what we have done is we have basically given the expressions for individual components of those matrices. So the components are basically given from this particular equation and they are here. There are some coefficients which we have used, alpha, which is equal to sigma divided by epsilon r epsilon naught. We have used the term c, which is the velocity of the wave, and obviously wi and wj are the 2D basis functions which we have used. So once we have this integrals, we can compute the individual matrices for t, b, g and f and plug it in. So you will have a simple form which is given here. One thing that is still not complete is we still have a second order derivative in time, first order derivative in time. So we need to find a way to manipulate them. So that is what we are going to do, but for that we are already in safe hands because we have an expression for a particular function, let us say of phi is equal to, so we are computing the value of the second order derivative based on this particular expression. So what we have is for the second order derivative del t square, so we are taking the value that is on the forward and the reverse and the central point. This tensile is something which we have already looked into in our earlier lecture on the finite difference. So we can also see that we can write the first derivative of t is equal to 1 by 2 delta t p of n plus 1 minus p of n minus 1. So what I have done is I have taken a central differencing between p of n plus 1 and p of n minus 1. So that is why I have 2t here. I can also do some kind of in between weighting functions. So I can say p of n is equal to some value beta multiplied by p of n plus 1 plus 1 by 2 beta p of n plus beta p of n minus 1. So what I have done is I have taken p of n plus 1, p of n and p of n minus 1, and I am using some functions of beta. In the earlier lectures we used the term r, or some of the ways in which we can compute r is also given by the PDE itself. One good approach is we can choose beta is equal to 1 by 4. So this is a good choice for numerical modeling. So if you choose beta is equal to 1 by 4, our expression which is here should be changed into a simple, more easily approachable form. So we are going to write it in a more easier form as follows. So what we will have is T matrix divided by delta T square plus the B matrix divided by 2 delta T plus G divided by 4, the entire thing multiplied by P of n plus 1 is equal to 2 divided by delta T square minus G matrix divided by 2 multiplied by P of n plus minus T matrix divided by delta T square plus B matrix divided by 2 delta T minus the G matrix divided by 4 into P of n minus 1 minus the forcing function matrix F. So this is nothing but what I have got in this equation. So I have taken this equation and I have substituted the value of the time stepping using the approach what I have explained in the time stripping algorithm. So I have chosen beta is equal to 1 by 4, and accordingly what I have got is an expression for the value of the update equation. So it is logical to see wherever there are T matrix, the value is a central differencing, which is basically the second order derivative of T is here, and then for B you have 2 T values, and you have the value for G which is given by 1 by 4, and they are all multiplying on the time stepping n plus 1. So what you have got in the left hand side of this equation is nothing but the update equation for n plus 1 step based on the values of P which is in n and n minus 1 step. So it is an explicit model to compute the value of the equation. Obviously there is some trade offs here, you have to compute these matrices T, B, G and F separately, but it is going to create a lot of computational effort, but this is the way you can model the finite element time domain for Maxwell equations. We will look more into this in the exercises, but at least now what we have got is a basic understanding of how to get into the Maxwell equations in the finite element method for explicit time stripping algorithm. We have done a lot of mathematics here, in fact too much mathematics. It is good that you at least know step by step how the process of doing update equations look like. I did not want to just stop at the point of saying that this is update equation, you can just fit it into a MATLAB code and do it, because the devil is always in the detail. So I wanted to give you step by step approach on getting to the point where you can use MATLAB to compute. Obviously when you do coding yourself, you will inevitably come into a lot of challenges where you have to find ways to do it. So with that we come to an end of this particular module and also the chapter of finite element itself. We have looked into the variational method in general, we looked into Rayleigh-Ritz method, we also looked into the method of weighted residuals and also into the method of Galerkin, and we also looked at various aspects of finding variational principle or the action of a particular PDE and how to go backward from a PDE to a action function. So in that sense we have covered quite a bit of work on the variational method, including finite element approach. We have seen also some examples that can demonstrate how the method actually can be executed using commercial packages like MATLAB. So with that being said, I would like to thank you for listening to this module, and we will look into the method of moments and applications of method of moments in the next modules to come. So thank you and see you in the next module. Bye bye.